Just to review, equilibrium expressions, what goes on the top? The products. And what goes on the bottom? The reactants. What do we do with the coefficients? They become exponents for the amounts of whatever substance we're looking at. What types of reactants and products don't go in equilibrium expressions? Solids and liquids. Remember, they don't affect equilibrium, so we don't put them in the expression. Only gas and aqueous. Okay. So, for this one, we're looking at two reactions, this one and this one, that have been done at, what's my temperature? 550 degrees Celsius. These experiments have been done at that temperature, and the equilibrium constants for both of those reactions have been measured. What does the size of the equilibrium constant tell us about the reaction? Whether the products or the reactants are favored. Remember talking about this last class? Now we're dusting off the Thanksgiving cobwebs. All right. What's like the cutoff point when we're looking at equilibrium constants? 1. When the value is greater than 1, that means the products are favored. Means we're going to end with more products. The amount of our products is going to be greater than the amount of our reactants. And when it's less than 1, that means that our reactants are favored, right? What type of value can K never be? Negative. Okay? Yeah, it's always going to be a value, right? And it'll be positive. Can never be negative, because if it's negative, that means you have a negative concentration or pressure, which doesn't happen. Okay? So looking at these two problems. So both of these, my products are favored, right? And these two reactions are going to add up to this overall equation. It's kind of like Hess's law, right? Back in Unit 3, wasn't that? Okay. So we want to find the K, the equilibrium constant for this reaction done at the same temperature. So we're going to have to manipulate my first two equations to make them add up to the overall. Okay? Just like we did with Hess's law. So what do you think we need to do? Look at the equations. Look at the overall. Okay, how are we going to, yes, we need to cancel things out. How are we going to do that? Okay, we're going to have to flip one of them. Which one are we going to have to flip? The first one, because we want H2O as a reactant, and it's a product in the first equation. So let's flip this first equation. When we do that, we get cobalt, which is a solid, plus H2O, which is a gas, goes to cobalt oxide, solid, plus hydrogen, gas. Now, in Hess's law, back in like thermochemistry, when we flipped reactions, what did we do to the sign of our delta H? We flipped the sign. If it was negative to begin with, we made it positive. If it was positive to begin with, we made it negative, because the opposite process did the opposite thing in terms of endo or exo. Now here, we said we can't have a negative K value. So instead, we're going to take the reciprocal of our original K value. Can you please stop? We're going to take the reciprocal, okay? Because mathematically, for the first reaction, my products are on the top. The cobalt, well, actually, really just the water is on the top and the hydrogen gas is on the bottom. If I flip it, now hydrogen gas is on the top and water's on the bottom. So my whole equation gets flipped over. So my K gets flipped over. So this K value is going to be 1 over 67. Okay. Are we going to do anything to the second equation? Nope. I'm just going to bring it down so we can cancel out the things we don't want. And that stays as 490. Okay, so when we add these two equations together, the cobalt and the cobalt oxide substances cancel out. So all my solids cancel out. And I get H2O gas plus carbon monoxide gas goes to hydrogen gas and carbon dioxide gas. Now, to find my overall K value, to find K3, we're not going to add the two K values together. Instead, we're going to multiply them. Okay, because that's all we've really done is we have combine these two reactions. Remember, in an equilibrium expression, everything's multiplication and division. So we really just multiply these two equations together in terms of the K value, in terms of the K expression. Okay? So we're going to multiply the two K values. So you're going to get 1 over 67 times 490, or 490 divided by 67. You're working too far ahead. Not even there yet. Remember, I'm recording. So 490 divided by 67. Let's keep it to, let's try to maintain the sig figs from the problem, even though I'm not a stickler about sig figs for K values, because most of the time you're going to be given them, not solving for them. So I'm not too worried about the sig figs of them, but when you are solving for them, maintain the sig figs from the problem. So what would our answer be with proper sig figs? 7.3. Because both of our original K values only had 2 sig figs. So what does that say about our overall equation, or our which part is favored for our overall equation? The products. Barely. 7.3 is not a very large K value. Barely favored, but still favored the products. We're still going to have slightly more products than reactants. Our numerator is going to be slightly larger than our denominator. About 7.3 times larger. Okay? Cool. All right. The next problem, there was actually part of this in the first video you watched, the one on equilibrium constants, one that was due the Sunday, like the night before you guys took your test. That one, the first Google Classroom Edpuzzle video that I think everyone in this class watched. So good job. All right, so this one was mentioned in there, which is what happens when we change the coefficients of a balanced equation. Okay, and I don't know why this is written like that. It should just say 1 NO. All right, so balancing an equation how you balance an equation will affect how the equilibrium constant is calculated. Okay, so we're told that we have a Kc of 1.3 times 10 to the 4th for this reaction. Let's go ahead and write that K expression. So on the top is going to be the concentration of NO. And on the bottom, it's going to be the concentration of N2 to the 1/2 and O2 to the 1/2. Okay, so for this reaction, as written, with these coefficients, we have a K value of 1.3 times 10 to the 4th. What if we had this equation and we wanted to find its K value? Well, let's write out the expression. What goes on the top? NO squared. And on the bottom is N2 times O2, right? So going from here to here, what did we do to the coefficients? We doubled them. We multiplied by 2. But what did you notice about all of the powers? So the exponents themselves were all doubled, but mathematically, what does that do to my values? Something raised to the first power versus something raised to the second power, we're squaring them all now, right? Yeah. So what are we going to do to the K value to find the Kc for the doubled equation? Square it. So for K values, you're always going to do reciprocals when you're flipping, and when you're changing coefficients, that is going to be the exponent that you're changing the K value by. Okay, so if we were going the other way, we would take the square root of our K value. If we were going from like this first equation and all of these were tripled, then we would cube it. Yeah, see how that works? So my new Kc is going to be 1.3 times 10 to the 4th squared. And what do you get? 1.7 times 10 to the 8th, right? Now, this equation as written, the one with like half, half, and 1, had 1.3 times 10 to the 4th as its Kc value. What does that tell us about the reaction? Favors the products. This one, when all the coefficients are doubled, we get 1.7 times 10 to the 8th. What does that mean? Favors the products even more. Favors the products even more. Okay. So what are my units on Kc? We don't report units for K values. For equilibrium constants, they technically have units. In this case, well, technically this one would not have any units because they would cancel out. But some reactions, they do end up having units. We just don't report them because it varies so much from reaction to reaction. Okay. Now, the whole purpose of this exercise was to show you that how you balance the equation will affect the K value. That being said, when you're given a K value, or when you're being asked to find it, you will already be given a balanced equation. Okay? Because I'm not going to do that whole thing where it's like, oh, well, you balanced it wrong, so you get the wrong, like, you know. If I'm giving you an equilibrium constant, which eventually we're going to work towards that, where you're going to find the equilibrium concentrations from the constant, you will be also given the correct balanced equation for that constant. Okay? So there shouldn't be any guesswork of, oh, does this one actually go with this balanced equation? Okay? Cool. What questions can I answer? Okay, so one last thing from what we were supposed to do last class, and then we'll get into today's lesson. Today's like a regularly scheduled programming. Last little thing is how to figure out which way the reaction is going to proceed in order to achieve equilibrium. So right now we've been talking about like what does that equilibrium constant mean in terms of what's favored. Well, now if we know the initial information, how do we know which way the reaction will go in order to reach that equilibrium value? All right, so we have this reaction. NOBr goes to NO plus 1/2 Br2. And it was studied at 350 degrees Celsius at several different initial concentrations. Okay? Let's go and take a moment to write the equilibrium expression for this reaction. What do you put on the top? Specifically for this reaction? Good. And its Kc value for that reaction as written is 0.079. Okay? All right, so we want to know which way will it proceed in order to establish equilibrium under the following under each of the following initial conditions. So for A, we're told that we have an initial concentration of NOBr of 0.1 molar, and NO and Br2 are both 0. Okay, so we have none of my products. Therefore, which way do you think the reaction will proceed in order to reach equilibrium? It's going to have to go towards the products. We're going to have to make some products, right? If we have none of these, we got to make some, okay? So it's going to proceed right. Or you could say towards the products, however you want to say it. But it's going to have to make products in order for this reaction to reach equilibrium, okay? What about for B? Why? Right, we have none of our reactants, so we have to proceed towards the left to make some. Okay, because remember, at equilibrium, you will always have a little bit of every single substance, because that's like the thing with equilibrium is that there's always a little bit of your, for example, this one, our Kc is fairly small, it's less than 1, so our reactants are slightly favored over our products, but we're still going to have some of both substances left over. Only those that are like super duper large K values, we're going to have like hardly any reactants left over. Considered to be negligible, we have like none left over. But a lot of reactions, you have a lot of both left over. both reactants and products. But yeah, so for this one, we're going to proceed to the left because we have none of our reactant. So if you ever have a 0 as your initial, as an initial amount, if you ever have none of one thing or of multiple things, that's always going to be the direction that the reaction will proceed in order to reach equilibrium. You won't have a case, there won't ever be a case where, say for this reaction, you only have NO to begin with. Like, it's not possible. Because then how would you know which, like, it wouldn't work. You have to have some Br2 as well. And then we have to proceed towards the left. Or, you know, okay, so you have to have either all of everything on one side or all of everything on the other side. It is possible to have something on both sides and still a 0, but that 0 can only be on one side of the reaction. Does that make sense? So wherever your 0 is, that's the direction you're going to proceed in order to reach equilibrium. And we're going to see that more when we do Rice tables, because that's going to help us figure out what mathematically is going to happen. Okay? Now, for C and D, what do you notice about our initial amounts? Yeah, we have some of everything. So we need a way to figure out which way is the reaction going to proceed. So that thing is called the reaction quotient. And this was in your guided notes. This was not part of the video, but it was in your guided notes, so this should be familiar to you. Okay? The reaction quotient is you're going to set it up just like the equilibrium constant or equilibrium expression, but instead of equilibrium conditions, you're going to use initial conditions. And then you're going to compare the reaction quotient to the equilibrium constant to figure out which way it's going to proceed. Okay, the letter we give for the reaction quotient is Q. So Q. So we're going to set up Q for letter C. The top is going to be 0.1 times 0.1 to the 1/2 over 0.1. Okay. Let's go ahead and solve what that Q is. I can't hear you. 0.0316? Is that right, ladies and gentlemen? I mean, I totally believe you. It's just 0.316? Gosh. You're lying to me. All right, so 0.316. All right. We want to compare this to Q. Let me show you a little trick, a little visual to help you remember, and then I'll explain why. Okay? So we're going to compare Q to K. Compare Q to K. When Q is less than K, imagine that these are the arms of a little dude who's saying, go this way. So when Q is less than K, it's like, go this way. All right? And when Q is greater than K, the dude's arms are saying, go this way. Okay? Now you have to compare Q to K. If you compare K to Q, it doesn't work. So compare Q to K and tells you which way to go. Okay. Now the reason why this works is, remember, equilibrium expressions are products over reactants. When Q is less than K, like in the case here, no, in the case here Q is greater than K. When Q is less than K, that means that we need to increase our value. We need to increase our product, or increase our quotient, because isn't that what a division, when you add something together you get a sum, when you divide something together you get a, oh my gosh, what's that called when you subtract something? Difference. Thank you. Oh my gosh. Thanksgiving cobwebs. When you divide something you get the quotient, when you multiply something you get the product. Yeah, those elementary school words. All right, so when you divide things you get a quotient. So we need that overall value to increase when Q is less than K. That means in order to do that, we're going to have to increase the amount of products. We're going to have to increase that top number. So we're going to proceed towards the products in order to make more of them in order to, reach the equilibrium constant. When Q is greater than K, like in the case for letter C, we want to decrease that value to make it meet where K is, because K is not going to change. Q can, because you just, as you reach equilibrium, Q becomes K. I don't know what that was. So in order to decrease Q, we have to increase the denominator, or the reactants. We have to make more reactants. Because when you're dividing something and the bottom number gets bigger, the overall answer gets smaller. Okay? So for this one, for C, since Q is greater than K, it's going to proceed, oops, there's another E there, proceed left. Because we need to make more reactants to make that bottom number bigger to make Q equal K. Cool? So if you need to, draw the little people. Some people, this way, you've got baby shark or mama shark, whatever it is. Okay, cool? Or Pac-Man. Okay, cool? Go ahead and try letter D. I'm going to pause this while you do that. Can I pause this? I cannot pause it from here. I need to adjust my screen. All right, so when you plugged in, when you set up this one, you should have gotten 0.05 times 0.1 to the 1/2 over 0.2. What'd you get as your Q? So close. So close to being paused during the bell. All right, so you got 0.079, which is, the equilibrium constant. Right? It's essentially the exact same thing, right? So what does that tell us about this reaction? It's at equilibrium. It doesn't need to proceed in either direction because they've already met. That's the whole point, is making Q meet K. Okay? Okay? K. Q. Rice tables. Let me explain some stuff about rice tables first. So RICE is an acronym, bless you, and it stands for reaction, initial, change, equilibrium. Now a few things about some of these words. Initial is talking about the initial amounts of your reactants and products. Remember, when you were writing equilibrium expressions, what types of units can you put in for your equilibrium expression? When you're calculating the constant, what types of values can you put in for your amounts for your substances? Molarity, so concentration, or pressure. So it's going to be concentration or pressure, not moles, not grams, not liters. So if you're given some of those things, you're going to have to, do math to find either concentration or pressure. Okay? So this is going to be concentration or pressure. And the same thing with the equilibrium amounts, but once you have it as once you've set what your initial amounts are, the equilibrium amounts will be the same units. Okay? Change is going to be the stoichiometric change. And what I mean by that is the balancing of the equation, or the using of the balanced equation that will probably already be done for you. Make sure you use the coefficients to help you figure out how much it's going to change by. You'll see what I mean when we do our first example. Okay? We ready to do the first one? All right. So we have this reaction. We have a 1 liter container holds 1.06 moles of H2 and 1.57 moles of CO at 162 degrees Celsius. At this temperature, the following reaction occurs. And then after equilibrium is established, analysis shows that 0.200 moles of CH3OH are in the container. And then we want to calculate the equilibrium concentrations of the two reactants and Kc. I'm cheating for a moment because I don't want to have to rewrite. Sorry, you guys do. I'm not sorry. All right, so I brought that reaction down just so I don't have to rewrite it, and that's going to be my R. So my R of my rice. So I'm going to set up a little rice table. Okay. I is my initial. The initial concentrations of these things. What was I given in the problem? Moles. So how do I find concentration from moles? Divide by my liters. In this case, it's 1 liter, so it's really nice and easy, but sometimes it's not 1 liter. So always make sure you check your volumes. I'm going to give you a hint. In a couple problems, we're not going to have 1 liter, and you're going to have to do some math, so don't get tricked. Okay? So in this case, though, the moles is the same value as the concentration, so I can just put in 1.06 for H2 and 1.57 for CO. I don't include units in my rice tables just because it takes up space. Okay? And really, honestly, all of this is algebra. Okay, so brush up on those algebra skills if you're a little rusty. I know some of you are in like high-level calculus where you might not have had to do some of this algebra in a while because you've been too busy integrating and deriving. Deriving. I'm going to start saying derivating. I hope, please start using that in front of like Miss Loy. I'm sure she would love it. Or Fitz. You're going to derivative? Okay. What is my initial methanol amount? No, that's my equilibrium amount. What's my initial methanol amount? 0. If it doesn't explicitly state that there's some of it at the beginning, you can assume it's 0. Okay? Unless it explicitly states it, assume there's none of it. Because we don't want people to confuse it with oxygen. Yeah. No. So it's not confused with a letter O. Because physics uses a lot of variables. But I only do it when I'm writing a 0 by itself. Like if you notice in 1.06, I didn't put a slash to that 0 because there's no one's going to ever be like, 1 point oxygen 6. No one's ever going to think that. But when it's a 0 by itself, I always put a slash through it so it's not confused with oxygen. Okay. My changes. Actually, which way is this reaction going to proceed in order to reach equilibrium? Towards the products, because we have none of my product. So that means we have to proceed towards the products in order for this reaction to occur, in order to reach equilibrium. So that means that the amount of my product is going to increase by some variable. Let's just give that the letter x. It's going to increase by some letter x. Both of my reactants, what are they going to do? They're going to decrease because we're proceeding towards the right, so therefore my reactant values have to my reactants are going to be used up. Not completely, not entirely, but partially. So they're both going to decrease. And like I said, they're going to decrease in the same stoichiometric ratio as my product is increasing. So CO is going to decrease by some variable x. And my H2 is going to decrease by 2x. Why did I put a 2? Because of the coefficient. So use the coefficients, and that's, how much it's changing by. So now my equilibrium for H2 it's going to be 1.06 minus 2x. For carbon monoxide, it's 1.57 minus x. And for methanol, that equilibrium amount is just x. Now, Eventually, in a few problems, you're going to be given the equilibrium constant, and then you're going to have to find all of these values. We're not there yet. You will always be given something about the reaction at equilibrium. Something about it at equilibrium, whether it's about a specific substance at equilibrium, like in this case, or the equilibrium constant. You have to be told something about equilibrium. I can't just be like, here's the initial conditions, find equilibrium, without giving you anything more. Okay? So you have to be given something for the end. In this case, we're told that we have 0.200 moles of methanol at equilibrium in the container. So what does X equal? 0.2. Because it's the same container, so it's still 1 liter. So we know that X equals 0.2. It's probably one of the simplest equilibrium rice tables you're going to see. So if X is equal to 0.2, we can find what H2 and CO's equilibrium concentrations are. So for H2 at equilibrium, it's going to be 1.06 minus 2 times 0.2, which is 0.66. What are my units? Molarity, and that's of H2. And then for CO, we're going to have 1.57 minus 0.2, which is and to find the equilibrium constant, you should write out the expression before you plug anything in. Sometimes, and it's kind of hard to tell ahead of time, but oftentimes they give you, it's a point on the exam just for giving the equilibrium expression. Always get in the habit of writing out the equilibrium expression before you plug things in. Okay? So, my equilibrium expression, I'm going to have what goes on the top? CH3OH. And on the bottom, H2 squared and CO. Okay, and now I'm going to plug in everything I know. My methanol concentration at equilibrium is 0.2. H2 is 0.66 squared, and then CO is 1.37. And like I said before, most of the time you're going to be given the equilibrium constant, so I'm not going to be real worried about sig figs right here, but let's try to maintain an appropriate number of sig figs. Don't give me a number with like 9 sig figs. That's just ridiculous. That wasn't this class when the kid did that. Never mind. So what do you get? 0.335? And remember, we don't report units on our equilibrium constants. Cool? Do you want to do one more together? Sure? Okay. All right, I'm going to move that over a little bit. So, we have this reaction. Notice how for this problem, we're given partial pressure information. We handle it the same way. We use it the same exact way as concentration, it's just pressure. Okay? So I'm going to set up my rice table. Honestly, the most difficult part of these problems is figuring out how you're going to get to your answer. So they're word problems. They're problem-solving skills are important. Figuring out what it is you have, what it is you're trying to solve, and the pathway that you're going to take to get there, that's all really important. How you're going to unpack the problem. You're going to get better at this as you do more problems. As we do more practice problems in class, as you do homework problems, maybe you jump onto Flynn Prep since you have a year-long subscription of that. And there's a whole unit of this on there. Jump on there, do those practice problems. Okay? look at your review book that hopefully you've already purchased one. If you haven't, I can give you some recommendations. You know, all that stuff. Go on the internet, look up like practice problems, okay? So just practice, practice, practice. Okay. All right. So setting up my rice table, what are my initial conditions of the different substances? For NO, what do I have? 0.526. What about for Br2? And for NOBr? 0. Again, if it doesn't explicitly state that you have some of it initially, you can assume that you have none of it initially. All right. So what are going to be my changes? For NO, what's it going to be? Minus 2x. Why is it minus? We're going to have to proceed towards the products in order to make the equilibrium be reached. And why is it minus 2x? Coefficient of 2. Good. For Br2, what's my change? Minus x. And for NOBr? Plus 2x. Okay. The signs for your reactants will be the same. The signs for your products will be the same. You won't have a minus and plus on the same side of the reaction. That just doesn't work. They'll either both be minus or both be plus. Okay, keep that in mind. All right, so my changes, we have, my equilibrium, we have 0.526 minus 2x. We have 0.329 minus x, and we have 2x. All right, what am I told about equilibrium that will help me figure out what x is? Yep, we're told that at equilibrium, the pressure of Br2 is 0.203. So that means 0.329 minus x equals 0.203. So we can do algebra to find x. So you should get 0.126 as your x. And now we can find the other two partial pressures and find Kp. Now, this problem, notice how it didn't actually ask me to find the other two partial pressures. All it asked me to find is Kp. But in order to find Kp, I need the other two partial pressures. So when you're reporting your answers, you only need to box or circle, clearly mark the answer that I've asked you to find. Okay? This also means that you don't necessarily have to write down what the partial pressures are equal to. You could just plug it into your Kp expression when you're writing it down there. You don't have to worry about reporting with proper units or sig figs. You can just deal with Kp. Okay. For our practice purposes, though, let's write down what those partial pressures are. All right, what do you get as the partial pressure of NO? Hearing different answers. So here you should get 0.274. And what do you get as for NOBr? 0.252. All right, so now we're ready to plug these into our Kp expression, which we should write. Now, I think I talked about this last class, which I know was a week ago. When you're writing Kp expression, so Kc is for concentration. Those are the hard brackets. Kp is for pressure, and those are soft parentheses. And you're using a pressure notation. So at the top, it's going to be a big P, because that means pressure of NOBr. And we're going to square that. In the bottom, we're going to have the pressure of NO squared and the pressure of Br2. It's just the proper notation for that. So the top number, we're going to plug in everything we know. And solve for Kp. What do you get? Are we there yet? Did I go too fast? You should get 4.17. Are these looks that I'm getting because this is like super simple? In most cases, that is. Good. Good. All right, number 8. Why don't you guys do this one on your own? I'll get it started for you. All right, I got it started for you. Okay. Why don't you guys try this one on your own? Only go up to finding KC. We'll talk about KP. We'll review that together. But get to KC. All right. Let me pause. All right, so now that you've had a chance to do this problem, let's go over it. So, so far so good? Yes, yes, yes? Okay. Why is it 2? Because of the coefficient. Good. All right. Yeah? All right. What do I do next?
You set the bottom equal to 4/5 of 2. 80% of 2. That's technically.
I set the bottom equal to 4/5 of 2. So 2 minus 2x, x equals 4/5 of 2.
2 minus 2x.
What?
2 minus 2x.
Stop dealing in fractions. This is science. So, we know that we have that. What does 2 minus 2x equal? Yes.
80% of 2.
How much has decomposed?
20%.
20% of that initial 2 molar has decomposed. So how much is remaining? 80%. Actually, it's not, because 4/5 doesn't have sig figs. Like, that's actually why I'm trying to steer you away from fractions, because fractions don't have sig figs. Decimals do. Okay? So, this should equal 1.6, right? Because that's 80% of 2. That's how much is remaining. So therefore, what is our x? 0.2. So now we know our x values here. Okay? So let's go ahead and write our KC expression. What goes on the top? Over. Okay, so now we're just going to plug in everything we know. What goes on the top?
0.2 times 42.
Over. All right, go ahead and solve for KC. What'd you get? Well, everything else was 3 sig figs. I just didn't write 3 sig figs down in my rice table. So I always look back at the original problem. Yeah, that's fine. So, KP, this is what we talked about last class. This is number 2 from last class. There is a formula that relates KP to KC. I said that of all the formulas, this one you probably want to memorize. Because even though they won't actually ask you to do serious calculations with them, there still have been problems where you need to know the relationship between KP and KC. Okay? KP equals KC times RT to the delta N. And delta N is the change in moles of the gaseous substances in the reaction. So how many moles of gases do we have on the right in this reaction? 2. We're just looking at the coefficients. We have 2 moles of gases on the right, and how many on the left? 2. So delta N for this case is 0. Yay, math. Which makes this whole thing 1, so it ends up canceling out. So Kp equals Kc. That has been a problem on a somewhat recent AP exam. That has been a question on a somewhat recent AP exam where you need to know that when you're not changing the moles of the gaseous substances, Kp equals Kc. Okay? Our next problems, our next few sets, are where we're going to be given the equilibrium constant and we have to find the concentrations from that. Now the process, we're going to set it up the same way. Okay, we're going to set up a little rice table. Though to find x, it's going to require a little bit more complex algebra. All right.
When you're doing the change in moles, is it products minus reactants?
So, what is my initial concentration of PCl5? Don't get tricked. 0.2. Because we have 2 liters. What about PCl3? 0. It doesn't explicitly state it, so we don't have any. And what about Cl2? 0. So therefore, what's my change? What are my changes? X, X, X? Minus X on the left. And on the right, what are they? Well, plus X and plus X, because these are addition and subtraction, not multiplication and division. So we're going to have 0.2 minus X, X, X. All right, let's write our equilibrium expression. What goes on the top? Okay, now let's plug in the things we have. Oh wait, we know Kc. Kc is 33.3. PCl3 and Cl2 are both what? X. And PCl5 is 0.2 minus X. So now, in order to solve for X, what type of equation is this? It is a quadratic equation. So, you could set, rearrange this, set it equal to 0, plug it into the quadratic formula, solve for your 2x's, and only use the positive x. Some of you might have a program in your calculator that does that for you. All of you should be using a graphing calculator. I'm going to show you a way that we can graph them. We can graph this to find our x. Okay? There are several. Honestly, I don't care how you find x as long as you find the correct x value. Okay, and as long as you're finding it. You get what I'm saying? Don't just look off of somebody's paper. That's not going to work. Okay? So however you find x, that's your prerogative. But I would use the fastest method possible because everything you do for a grade in this class, like on a test and stuff, it's all timed. So you want to find the method that is the quickest for you. Okay? I find the quickest to be graphing. So what I'm going to do is I'm going to do a slight rearrangement of this equation because we were having some issues before Thanksgiving break where even though I was plugging in the same way as another kid, some calculators just didn't like the fraction. So I'm just going to do a quick rearrangement. I'm going to set these two equations. Okay, and I already have my calculator thing up. And what I'm going to do is I'm going to graph both equations. Graph both sides of the equation. So there's my first one. And my second one's just going to be x squared. Okay? So I'm just going to graph them. Mine's a little more zoomed out because I didn't reset this after last class. If yours is more zoomed in, you can press zoom and then 0 to zoom fit. I don't care. There are technically 2 points where these graphs these lines intersect. These curves intersect. We only care about where they intersect in the positive x area. Okay? So technically, there's an intersection like way up over here that we can't see on the graph. We don't care about that one. That's a negative x. We care about this one right here. So the way that you can find that is second trace. Nope. Second trace. There we go. Didn't hit second. And then find the intersect. Now you could also have taken my original equation, solved for 0, graphed just one equation and find the intercept, the 0 values, and just taken the positive x. But it's really up to you. I find the intersect better. I like the intersect. So it asks you to identify your first curve, your second curve. It wants you to make a guess. Don't ever move this because sometimes if you get too close to the negative x intersect, it messes it up. Enter. So enter, enter, enter. And it tells us that this intersects at x equals 1 or 0.198. 88 blah, 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 and 0.0395 for the y. We don't care about the y. We only care about the x. So our x is 0.199. And how you get to that x, I don't care. As long as you get there. Right? And you get there correctly. And on your own. Maybe with the use of a calculator. But not the use of a friend. Okay? Or an enemy. So now that we know x, the question was calculate the equilibrium concentration for all species. So PCl3 and Cl2, they're the same thing because they are just x. So that's 0.199 molar. Yep. And then PCl5 is 0.2 minus 0.199, which is 0.001 molar. So we're going to have barely any PCl5 left over. No, because we're subtracting. So you're going to maintain decimal places when you add and subtract. Okay? Go ahead and, I'm going to leave number 9 up on the board, but go ahead and flip to number 10. What do you notice about number 10 compared to number 9? So I goofed, right? I have the exact same problem twice, right? Wrong. I don't have the exact same problem twice. What is different about number 10? We have some chlorine gas to begin with for this next problem. So the equilibrium constant is the same because it's the same reaction at the same temperature. I'm starting off with the same initial concentration of PCl5, but I also have some Cl2 in that flask to begin with. Okay, so I'm going to set up my rice table almost the same way. So PCl5 is still 0.2. PCl3 is 0. What is Cl2? You almost got tricked. Still a 2-liter container. All right. My changes are still the same, though, because I still have a 0. I still need to proceed towards the products to make this reach equilibrium. So this is still going to be minus x plus x plus x. And this will be 0.2 minus x, 0.5 plus x. So in writing my equilibrium expression, it's the same thing. when I plug it in, I'm going to find a different x. My x is going to change slightly. Do you think my x is going to go up or down from what I had originally? It's going to go down a little bit. Because I don't have to proceed as far to the right in order to reach equilibrium because I already have some of my products. Oh, I keep doing that. I keep writing Kc instead of 33.3. 33.3 equals x times 0.5 plus x over 0.2 minus x. Yeah. And just like with the last time, what I'm going to do is I'm going to partially solve my equations. My first equation is going to actually still be the same because 33.3, if I bring this over, it's still going to be 33.3 times 0.2 minus x. But instead of x squared, it's going to be x times 0.5 plus x. Yeah? And now I'm going to bracket. That line stays the same. My parabola shifts a little bit because now I have a y-intercept. Can't even really see it on this graph because it's so zoomed out. But the intersection point did change slightly. So remember, second, trace. That brings up calculate. 5. Enter, enter, enter. You don't ever want to guess. Just tell it to calculate it. And what is my x now? 0.196. It was 0.199 last time. Now it's 0.196. See how it changed just a little bit. So to find my, so PCl5 is going to be 0.2 minus 0.196, so 0.004. PCl3 is what? 0.196 molar. And Cl2, 0.656. 696? Yep, I can listen. And math, 0.696. Cool? Questions?
Is this going to be like similar to one of those, if you can do this, you can do all?
This problem, if you can do that, no. This one's not very complex. No, this is like a basic problem. Yeah. Like, you should definitely be able to do this. All right, so why don't you guys try number 11. Let me put that one up on the board for y'all. Why don't you guys try this one? Process-wise, it's the exact same, just different numbers. Okay? Here, I'll get it started for you. You love when I do this. I'm going to get it started. Help you out a little bit. There you go. It started. Yep. Helps you out so much, right? So go ahead. I'm going to pause this while you guys try this one. Pause. Or push record, I should say. All right. So it worked. All right. So what is my initial Cl2? 0.4. What about F2? And CLF? So as I said during the pause break, we have none of F2. That means the reaction is going to proceed to the left. So that means that my reactants are going to be my plus x's this time. And my product is going to be my minus 2x. So it's changing the signs. If you solve for a negative x and you got a negative x in this problem, that's because you probably forgot to do that. Okay? You might have just gotten the negative of the correct x. We'll see. So equilibrium, this is 0.4 plus x, this is x, and this is 7.3 minus 2x. All right, so let's write our equilibrium expression. What goes on the top? That's an L. That's an L. Right on the bottom? Did you think that was Ci2? You know, it's an L. Don't forget that chlorine exists. Poor chlorine. All right, so now we're going to plug in what we know. 19.9 for my Kc. That's going to say 19.9. My top is 7.3 minus 2x quantity squared. Why is there so much chatter? My bottom is 0.4 plus x times x. All right. So back to my y. Both of these equations no longer apply. Okay. So I'm going to bring this amount over, and I get 19.9 times 0.4 plus x times x. I mean, yes, you could factor some of that, but why waste the time? I feel like it might just be easier to type it, right? And then my top is going to be 7.3 minus 2x squared. Yeah? Okay. Graph. And again, we have two intersection points, but we only care about this one. This one is going to be negative. We don't want that. We want this one. Okay? So, second trace. Enter. Enter. See how it's closer to this right now, so just leave it alone. And it should find that one. And it did. What is my x? 1. 1.00. So, my equilibrium concentrations of everything are F2 is going to be 1.00 molar, right? What is Cl2? And CLF? 5.3? Good, we can do math. Cool? We're going to stop there for today. Control your excitement.